So I'm super happy to introduce our next speaker, good friend Andy Moderow. Andy lives in Anchorage, and he's a frequent public observer and volunteer with the Chugach National Forest Avalanche Center. He was on the Avalanche School Board for 9 years and taught Snow Science 1 at APU classes and adjunct. This presentation is one of several projects on a 2-month volunteer internship with the Chugach Avalanche Center during the 2021/22 season. And I would just also like to add that, really can't overstate how helpful Andy is for everything we do at the Avalanche Center. Whenever we know he's getting out, it almost makes it feel like there's less stress on us for a field day because his odds are just as reliable as ours. It's maybe better than mine probably most of the time. Andy once told me that he prefers the big bowls than he does to ski in the backcountry. And also a fun fact, this summer Andy made it to a Taylor Swift concert as well as a weekend.
Oh,
He's going to give a presentation that he already got to practice down at ISSW, so it's good we got the warm-up one, but here's the reveal.
Yeah, thanks, Andrew. This is not as scary as 700 people and COVID was all around us. One of the more terrifying experiences. But no, thanks. So the plan for the next little bit, we're going to do a paper that I wrote up with John Sykes. Pause for a few questions, and then there were 4 other papers that were really awesome on stability tests done and then, so we're going to talk about those. And to get it done, I'm going to probably talk fast, not that I have a choice in this matter. Here we go. So, stability test craftsmanship, does it matter? We've all been in a snow pit after conducting a stability test. The failure was very notable. When you pull the top of the column off, right? Take a look at the weak link. You put that column off to the side, sometimes you look at it and go, wow, I did a perfect 30 by 30 compression test. Or wow, that's a perfect 30 by 90 centimeter block for ECT, right? And sometimes you put them aside and go, ooh, that was not my best one. Does that happen to anybody in the room? Yeah, right? So the question that this project seeked to answer was, does that craftsmanship error? The particular type of craftsmanship error evaluated was irregular blocks that change dimensions with depth. And with a taller column comes more of a chance for variation to occur. So you'll see in this slide, the irregular block compression test was performed, tapering in or out by 1/3 to the weak layer. And then an irregular block ECT was performed, again, with surface dimensions proper, but with a taper by 1/3 to that weak layer. To compare the results, we also performed a set of under and oversized compression tests. These were sized to equal the weak layer in the irregular block compression test. Previous research had found block change dimension by about that much can actually make a variation by a tap or 2 in stability test results. So with that data, we could then try to figure out whether or not a regular block shape could increase variation as well. For a field location, it was a kind of a weird winter, this winter in March of 2022, and we found the ideal project parameters at Finale Park in the Yonder Valley. This is a very continental snowpack, for those of you who have not been there. It was particularly deep that year, at 1 meter total snow. But there was a layer of advanced facets and depth fold down, pretty close to the ground, and an 80 centimeter slab above it. And so with that, we found that relatively deep and weak layer, and the project was proceeded. Field days, there were 3 of them. They were all conducted by the same observer. I went up there and did a whole bunch of tests. And we did that to also reduce variation based on observer. And we're going to talk a little bit about that in one of the next papers to cover as well. But the procedure for cutting these blocks, you see a giant snow saw on the right, a vertical cut would be made, check with a level on the front. Then 30 centimeters behind that, I would make a second cut. And then using a ruler and level, I would lay out a properly executed compression test. The oversized one you see in the middle, and then on the undersized one you see in the right. And the blocks were tapered in 2 dimensions. And that was intentional to keep block symmetry. We weren't testing whether or not an asymmetric block would pull and trigger a weak layer earlier or later. We wanted to keep that block symmetry like a regular compression test. Once those blocks were laid out, regular isolation with a standard snow saw would occur. For the extended column tests, Basically the same procedures were used, but that giant snow saw was used to cut and isolate a 90 centimeter long block instead of stands and snow saw. So we'll get on to the data. First, on days 1 and 2, I did 50 repetitions of each block shape for the irregular block compression test. 141 of them failed by 30 taps. This was a little bit of a problem. 31 taps, and going into overdrive is kind of hard to calculate averages. Since one of the goals was to evaluate whether or not you need more or less taps based on block shape, we had to figure out how to deal with those results. In the end, the 9 tests, and I will say they were all in the oversized regular block. Those CT end results we coded as 31 for the purposes of calculating averages. So here's the data. The difference, the properly executed CT on those days failed at 21.1 taps on average. The oversized or regular test failed 4.1 taps later. And the undersized test failed 4.7 taps earlier for a difference of 8.8 taps between the oversized and undersized reports. Big shout out to my co-author, John Sykes, for this analysis and for reviewing the statistics and also teaching me science throughout this process. He conducted a 2-way analysis of variance tests, and we looked at the adjusted p-value, which tells you whether or not these results were significant. 0.00 from the tested p-value was very good, very significant, telling us that these results could be counted on as experiments. You also see the great plots. It shows you that the undersized regular blocks generally failed before transitioning to a shoulder force. And the oversized blocks generally happened after transitioning to shoulder force. Indeed, 90% of the tests failed in moderate or in hard based on block size. So it shows you the average test was failing on the first tap from the shoulder. There's a pretty big difference based on block size. Okay, moving on now to the under and oversized vertical columns. On day 3, I did 20 of each of these block shapes. Again, these vertical columns were sized to equal the weak layer size in the first test. There was one problem. The weather forecast looked good. That was one of the test parameters we were going for. Like there was any snow on the horizon. We did get 15 centimeters of new snow overnight, a quarter inch of snow water equivalent. So that is a variable that did change between days 1 and 2 and this third day. And again, there were 2 CT end results of the 60 test performs. And again, they were all in the oversized block. And we put those in as 31 for purposes of calculating these averages. So here are the averages that we see. On this day 30, a standard properly executed CT failed at 23.2 taps. The oversized block failed 2.6 taps later on average. And the undersized block failed 3 taps earlier than the properly executed CT. That's a difference of 5.6 taps from over to undersized. Again, we did the ANOVA test, and the adjusted p-value was a little higher. It was 0.01, or equal to, or just about that, for both the under and oversized tests. Still statistically significant results, so we're pleased to see that. The 95% confidence intervals around the averages for these blocks, a little bigger than the last one, plus or minus 2.5 taps. So again, strong results showing that block shape does influence results. So finally, comparing, and before we move on to the extended column test, comparing these, we had a spread of 8.8 taps for the irregular block shape. We had a spread of 5.6 taps for the vertical columns. And this suggests that the regular block shape may increase variation beyond just changes to the size of the block as well. So that was one of the first things we concluded from reviewing this data. Moving on to the irregular block ECT, these were more time consuming to make, and they were conducted on days 2 and 3. Again, that storm came in and changed the snow back a little bit on day 3. But on day 2, I conducted 5 of each block type, you see picture. And after getting just 1 failure in a standard ECT and no failures in the oversized sample, I discontinued the oversized block so I could maximize repetition of the regular ECT and the undersized block. Did 15 more of each of those. So we didn't do averages for all these results, but the undersized or regular ECT failed with propagation at an average of 22 taps, 100% of the time, 20 out of 20 tests. Contrast that to standard ECT, and only 3 out of the 20 tests failed. 17 of the 20 had an ECT result. In the oversized or regular tests, as I mentioned, all 5 of them did not fail. So you don't need to necessarily calculate averages to show the difference in result for this particular slope map with the extended column test. Now, we'll get into some caveats here shortly, but that was the result. The takeaways, as mentioned, the irregular compression test block shape, average results fell well within moderate or hard force. And as practitioners, we often use those broad categories to convey what we see. And with the ECT sample, the block shape determined whether or not you had ECT X in the vast majority of cases, or ECT P 100%. So pretty stark differences for this particular sample. That's a huge caveat with this entire study. This was one location, one snowpack, and one type of error testing, right? We don't know if these trends hold for different weak layers. We don't know if it's slab weak layer combinations. We don't know if the exact same weak layer very much equals to the same variation. We also don't know if a standard CT was failing at 5 times, right? Only that one. So huge caveats. One of the benefits of this project was the repetitions that enabled strong statistical results. But one of the drawbacks is there's still huge questions about that. The other things that the test did not test is, what about asymmetric columns? What about columns that aren't perpendicular to gravity, right? And what about columns that aren't fully isolated? Anybody ever not fully isolated a column? Yeah, it happens, right? So those are other types of craftsmanship errors that do occur in the field that can change things. And then finally, how do these errors and variations by observers, when you're doing some of this shortly, how do they compound? If you're a light tapper, you don't fully isolate your block, and it's undersized. Where does that go, right? So at the end of the day, this is a tiny little piece of research, right? It was just one type of area that was explored. But blocks are easy, and craftsmanship error and block size are easy to identify in the field. We all have what we need to be able to look at our work and say, was this proper or not? You don't need to carry special tools. So I think that's a case for keeping an eye on craftsmanship. The other thing I found in preparing for this whole experiment was that I had some personal tendencies. My blocks tapered in as I cut them. I think it was due to fear of not isolating the block, that I would just kind of get a little smaller as I go down in depth. And a few centimeters on each dimension can be used to the weak area surface area of that type of stuff. I tested a third in this, and that was a pretty exaggerated difference, but little small areas that are your tendencies you can learn and correct all the field. So that was valuable to me personally. And then finally, just another takeaway for practitioners: if you do that test, you set your block aside, and you look at it and go, wow, that's ugly, you might want to redo it before you tell anyone what you thought. So for this first paper and the research, again, thanks to co-author John Sykes for all the help on this paper. Thanks to Ava, Wendy, all of who couldn't make it today, Andrew and Wendy, my daughter said Wendy. Just thanks to the Chugach Center for all the help over the years and for feedback on this project. I'll pause here, catch my breath, and answer a few questions before we go on to 4 more papers. Maybe we'll have questions. Yeah, great question. So the question was, for folks who couldn't hear, would slope angle potentially change these results? Previous research into compression tests and extended column tests have generally found that slope angle does not impact the results much. So while I can't say conclusively, I think generally in the field as practitioners, slope angle, what was used to be thought of as something that was very important, for these 2 particular types of tests, generally it's accepted that they're pretty similar.
I have a question related to different tools for cutting tests. I'm just kind of curious if you can speak generally to what you've seen, like saws versus strings and probes, and what you've seen sort of in this context.
Yeah, great question. I will say, making that snow saw for the test, I experimented and thought about different ways to do it, and having a very heavy saw that was very long made it so once it started to make the cut, it did not vary side to side. The blade being really thick help me track and keep straight from top to bottom. And you see some snow saws on the market that you carry in your backpack, some that fit in your shovel, right? I think those things probably have a tendency to wander more than the saws with longer breadth to it. So that helped a lot. I was worried I couldn't cut the ECTs consistently, because it's kind of hard to put that long saw up there and make it cut clearly. But with a 6-inch long saw, that helped. I think cords are obviously a different tool too, but that's where I always have fear of not isolating. That was not a fear with a giant 20-pound metal saw. That was going to be an isolated block, whether I wanted it to be or not. So it's a couple observations and stuff.
So, for tests, we're looking for consistency. Are you aware of any other research that shows accuracy between the different size blocks that you can
That's my third of the next paper that we'll be going through. So let's hold that question. It's a great question. I mean, again, this was just a simple little dumb geared taps change with the size of the block, but then getting to what we do with that data.
Can you repeat the question?
Yeah, the question was whether or not this is about accuracy, but then what does this tell us about stability and nearness? What are the lessons? And that was the Marion paper we'll talk about. All right, one more question on this one, if anybody has any, and then we'll move on.
You've done enough teaching, see what's new, good, and bad. Is there like something that you see regularly?
Yeah, you know, I actually haven't done a whole lot of teaching. There's many more people who've done a lot in this room. I don't know if anybody has a quick answer to shout out on what they've seen in the field for type squares.
Yeah, you're studying, whether it's we have preaching, that were particularly that failed to
Awesome, and that was from Nancy. A square plumb and 30 by 30 is what she said she's taught over the years, and often seeing narrow room that's failing earlier. Narrow at the bottom, which I personally had a tendency by a centimeter or two. When I thought I did it perfectly, I would be narrow at the bottom. So it's a sign for you all to go out and do bits. The other thing is I did my first bit last weekend, and I started cutting the block, and I'm like, wow, now I really have to be accurate. Now you're doing a talk on the importance of accuracy. It sucks. We'll leave that for later. All right. Well, we're done with one paper. Now I'm going to try to walk us through 4 more real quick. And these were papers and posters or presentations at ISSW. This first one was one of my favorites. It was a poster that compared stress measurements in snowpack during compression tests, and particularly whether or not there is stress at the weak layer differences by observer and by different weak layer depths. And on the right of this slide, you'll see a photo of a block sitting on a scale and stress gauge. And so a bunch of different observers bumped on that block and helped us and the authors, Ricer et al., get these results. So here you see the median stress levels and their ranges around the around the medians at a 20 centimeter block on top of that scale. Just to orient you to this graph, across the bottom we have the number of taps. The first tap from this is over there on the right. The 30th from the shoulder is over there on the left. On the vertical axis, we have the stress at the weak layer. The black dots are the median amounts of stress put on the weak layer out of a sample of different observers dumping on the block. Right? The lines show you the trend over time, and the gray area is the interquartile range. That's like the middle of the results. Right? If you split it up into quarters, that would be 50% of the data. A couple cool things about this chart. One, you'll notice that interquartile range is smaller for hand taps than from the shoulder. This led the authors to conclude that, in fact, there's less variation by observer when you're doing hand taps and shoulder taps. This is particularly important for really unstable times when you're trying to get data at what right? So that was one thing. The other thing thing you'll note is the trend of results. You'll see that each tap in the hand tap gets a little more stress on the snowpack. And so the authors concluded that this is likely due to the shovel slowly penetrating the block and compacting the snow and transmitting more stress to that weak layer as the test is conducted. So within hand taps, the first hand tap puts less stress on the snowpack than the last one. And that was pretty cool to see quantified, right? But it made the authors stress the importance of completing every single tap, not skipping them as you go through and do these tests. The final thing that I thought was really cool, when I was in Denali doing 255 tests in 3 days, I was thinking, not all tests are equal, right? We do that by design. Wrist, elbow, and shoulder. This quantifies the difference amount of force by those changes. So that's pretty cool to see. So I encourage you to look at these papers. At the end, I'm going to have all these papers up and take a photo of them and look them up yourself. There's a lot more to them than just this, but a couple highlights. Also, this paper took 62 people and had them tap on a shovel attached to a stress temperature. And this is a little bit different. It's kind of the same orientation as the last one, except that you see green dots for each of those 62 observers. And once again, you do see a cluster of green dots. It's smaller at the hand taps than they are for the shoulder taps. The authors also looked at whether or not your height, your weight, your arm length, and things like that change the force that you tap on the shovel. And they did find a correlation between taller, heavier, longer limbed people tapping harder than smaller people. So I think if you're as tall as me, that means we need to listen to Rage Against the Machine before you have your test. I don't know what the answer is, but that was my experience. So a cool paper. In the end, stresses that reach the weak layer do vary by observer and by snowpack. They also did a 50 centimeter block on top of that scale and found different stress reaching the weak layer. But overall, they found surprisingly low variation, particularly for the early loading steps, which is important because that's when instability is the highest. Okay, there's the first of our 4 papers in this study. Next, we're going to go to comparing the effectiveness of the ECT, PST, and CT for assessing snow stability. Alex Marienthal and others wrote this paper, and it explored how accurate these 3 tests are at predicting slope stability and how results impact avalanche forecasts. So here you go, Blaine. This is the one you were waiting for. All right, so this paper in particular gathered 2 data sets. One was from professional avalanche forecasters. Not only pit data of when stability tests failed, but also surveys about slope stability impressions before and after conducting the test. So that was the first data set. The second one was all snow pilot pits with a stability test result in them and stability indicators of nearby slopes, right? Because the question is, do pits tell us much about slope stability and how accurate they are, right? So that second data set was 3,300 pits from Snowpilot. This is the online database that gives you the images that you often see in observations. Many of us use, right? And that's what they use to conduct this research. All right, so this paper, like many papers in the past, used a contingency test where 2 variables are compared to one another in a very binary way, right? And so ideally, tests would end up, stability tests and slope stability, if the test is true and in that green box, then it would be unstable test, unstable slope, everything's great, right? Or you have the opposite, you have a stable slope. The stability test tells you things look stable at that point, right? That's the ideal that we're looking for. So this paper was evaluating how often do we end up in that false area, either as unstable slope, but our snow pit say it looks like a stable slope back on the box. So, real easy, right, to put a stability test into unstable or stable, right? CT17, is that stable or unstable? How many people think it's stable? Put your hand up, is CT17 stable? All right, unstable, everybody thinks, oh, it's not one unstable. Anybody think unstable? CT17. What's the fracture quality? That's a good question. Okay, I'll give you a fracture quality. CT17Q2, stable or unstable?
Yes,
Stable, right?
All right, let's try this one. CT27, stable or unstable? Hands up for stable. All right, it was a CT27SC. Stable or unstable? Okay, so This thing goes up and down. All of these answers are correct by past research into stability tests. A compression test and what is stable and what is not stable. Prior research reviewed by this paper. Each of those ones I read off have been classified as stable or unstable for the purposes of doing contingency tests on unstable time. So that's why I raised it. Like, you're kind of forcing things into this binary system that don't necessarily fit. Likewise, whether or not a slope is stable, there's a variety of ways to do that, right? You can do that by other red flags that were evident in the area of the pivot step. That's a way a lot of previous research has been done. Right? Also, some papers did whether or not you could artificially trigger it. So it was a very defined question of whether or not it's stable. So this paper calculated stable or unstable for stability tests in a whole bunch of different ways. So read the paper if you want all the different ways. But as a result, you see a range of results presented. So if you look at that red box, and it's red instead of yellow, because these are the days where you do the stability test, looks good, but the slope is actually unstable. Perhaps a worse error than not seeing the slope that actually was stable, which is that upper one's yellow. But you'll notice in particular the compression test, false stable rates of 8 to 45%. Now, 8%, you're like, cool, the CT nailed it, right? Way more effective of a test to not have false stables, right? The flip side of that false stable rate being low on that 8% level is that the test, with that way of viewing it, had a roughly 80% false unstable result, meaning that 4 out of 5 slopes that were actually stable, the compression test said was unstable. So this led the authors to conclude the compression test is actually a fairly conservative test. And so it's, even with fracture character and shear quality, it's being noted about it. Propagation SAW test, really interesting finding from this paper. There's a difference in the false stable rate between the pro sample, and these are the pros doing the pits, and the all snow pilots. And the authors kind of dug into that a little, pun intended, and decided that it's probably due to execution errors, either in choosing when to conduct the test, or also in performing it correctly in the field. And that might have been the result. So for practitioners, if you're teaching back 2, and they're like, EST, ECT, which one should I use? If the pits are pretty ugly, maybe say ECT. It's harder to screw up. And then also, like, when do you apply these tests? Finally, as mentioned in the pro sample, there was a question both before and after how stable is that slope. And about a third of the time, professional forecasters change their stability rating of nearby slopes after conducting the tests. So that drove one of the conclusions that, because we see avalanche forecasters, and these are the people who have been in the field for many years doing this research, taking a look at the snowpack, it's clearly a tool that is relied upon to calculate stability of nearby slopes. But at the same time, you get false stables a lot. So it's something that's, at the end of the day, the authors didn't throw out stability tests. They show instead that false stable results mean you need to get the whole picture. The other reason the authors weren't surprised by these results is you go out there and dig a hole in the snow and look right here, and then we're trying to extrapolate to a whole slope, right? That's a scale mismatch. So it's very predictable that things aren't going to be perfect every time one does a stability test and tries to draw conclusions on that slopes. All right, that's 2. We got 3 more. All right, so this paper is comparing stability tests and understanding their limitations. And Carl Kirkland presented this paper. If you don't know this list of names, these are people who have invented these tests. These are people who refined them over the decades. And they don't have a logo, but if they did, I think it's fair to say they all have very good individual careers, but when they come together, they're basically the Wu-Tang Clan of stability test research. All right, so this paper started out by comparing 4 different types of tests: the Chugach, the compression test, the extended column test, and the propagation SAW test. They considered how they do at telling us information about snow layering, failure initiation, like how likely will a fracture begin underfoot, and then whether or not when that occurs, will it propagate and potentially produce a slab avalanche. So on the layering front, the authors found, and this is actually from older research, that all the tests that compress snow from the top, really do a good job at giving you information about where there's a slab and where there's a weak layer. The propagation saw test is not designed to give us that information. In fact, it's a test that you use when you already know the weak layer and have questions about propagation. In the name. The next question the authors dug into, and previous research had dug into, is failure initiation. Again, there's kind of points for those tests that compress the weak layer from the surface, by giving us the best information of failure initiation. This is due to the fact that this is how we often trigger avalanches, when we're on foot or on snow machine. Propagation saw test does give you a little bit of information of how touchy the weak layer may be, but it's not designed for that. So you get some information, but not much. And then finally, for the question of crack propagation, all tests do give you some information. And to the quip earlier, like, what was the fracture characteristic of that CT? But fracture character and shear quality were designed to help give some information about propagation propensity. But really, it's those tests of bigger blocks that tell us the most about that. The authors then asked the question of, is there a most effective test? Right? So it's getting back to Blaine's question and then the previous view. And they, looking at the data, discussed the fact that you're looking at 80% accuracy of the tests for any of the tests. And there's not a best in any of the scenarios, really. It's really going to be situation dependent. So in their review of the literature of contingency tests and tests that look at stability test results, very sort of stability. They're all valuable, just know the limitations. The limitations the paper explored and things to keep in mind in selecting the tests that you're going to perform. How deep's the weak layer, right? If you have a slab that's very shallow, with a roosh block, you might step onto the block, the initial load step, and step right through that weak layer, right? So that might rule out that test. At the same time, when we're tapping on blocks from the top, that doesn't necessarily trigger a very deep weak layer. Literature often says 130 centimeters deep with limitations for things like compression tests. There's a lot of people in the room who don't trust them more than a meter deep, right? Like, shout out, how deep do you trust compression tests? Meter? Are we good with the meter? Yeah, I see some hidden outs for a meter. Yeah. It really is a question. That's where a propagation saw test. Another limitation of tests, and the authors talk through, is understanding those intermediate tests. What does a CT17 do? Right? And that's just something to think through when choosing tests and how to interpret them. The question earlier about slope angle dependency. Generally, there's no issue with slope angle, with extended column tests, compression tests, and with the American style PSA. It turns out that in other places, blocks are often called perfect rectangles regardless of slope angle, and that can cause some shear downward when you conduct your PSA. That actually can change your PSA results. But when we cut ours perpendicular to gravity, generally slope angles don't seem to be too much of a factor. But it's a concern for the roosh block. You need a little bit of slope angle. Research has said to conduct a roosh block. Prior knowledge of a weak layer is necessary for a PSD. It's not for a compression test. And finally, the time to execute a test. I like digging bits a lot, but even I don't want to do a roosh block. It takes a lot of time. Right? We only get one test. So another factor to choose test carefully. And the authors throughout all these papers remind us that stability tests do not equal avalanches, right? We all know the saying, stability tests, you don't go to them for permission to ski a slope, right? This is something that you only use in situations like that, and everything else is telling yes. It's a final thing for confirmation. We don't look at stability tests solely for making decisions about avalanches. So, conclusions from these authors, ECT is useful in many situations, both for experienced and inexperienced people alike. Roosh block is more of a feel, and it's a bigger test. So again, benefits to understanding propagation with bigger tests. They take longer to dig. PST is useful for when you know the weak layer, if you're comfortable knowing when to do the test and execute it correctly. But a particular shout out for using it for deep weak layers. And compression tests finally are useful for crack initiation, weak layer identification, and near surface snow instabilities. Another point from the CT and how fast they are. Finally, the authors, we talked all about these tests, the scientific parameters, but at the end of the paper, they noted that slowing down, digging a hole in the snow pit, snowpack, getting a feel for the layers, right? That slowdown is good too. It causes people to talk and think through what's value just in that, let alone where you're doing the tests. So, we're to our final quick one. This was a poster, actually. I think it might get a conversation going. That's the goal of it. Pros and cons of snowpack tests and recreational avalanche education curriculum. This paper was just trying to start a conversation about the complexities of snowpack tests and their underlying reasons for design. You all can read. You can also look up this paper. So I'm not going to go through all of it. But I'll just highlight a few benefits to recreational education that this paper highlighted. It presents and prepares students for areas without avalanche forecasts. Right? What do you do if you have no data? They can be useful for illustrating spatial variability. Dig here and dig there, and see differences in structure. Students expect to learn them when they have avalanche. They also visibly represent the hazard. I think we all remember like getting in a snow pit during an avalanche course. Wow, this is how it works, right? I mean, it really is quite fun. So all benefits and useful for understanding. Drawbacks that the poster highlights as a result, risk of result in this application. Do students, especially like at a level 1 level, are they going to apply what they get from the snow pit correctly? Will the snow pits that they dig and the tests that they conduct be relevant to the actual conditions? And then finally, I think this is the most interesting one, as a focus of pits in recreational education, overlook fundamentals of hazard evaluation and decision making, right? We just spent 25 minutes talking about snow pits. This is a pretty good crew, right? What about a level 1 student who are going to do 3 days and that's it? And then they're going to look at the avalanche bulletin every now and then. Right? Is that the best use of their time? So these are all questions that that poster presented. I think it's kind of interesting to think through. And that was a quick whirlwind tour of 4 of my favorite posters and presentations from high school. So with that, if there's time, any questions? If there's not, thanks a lot.
We're going to postpone, don't go anywhere yet, Andy. We're going to put questions out, maybe take your social afterwards. And then hopefully fuel the fire for some argument too.
Did you say there was a final slide?
If you want to read these, take a photo of the slide. Whenever I'm looking for the ISSW library, I Google it, so that's the instruction at the top. And here's my email if you want to continue the conversation.
Cool. But before you take off, Andy, I think Alice, maybe want to update. Yeah, a little thing for you.
Mostly, yeah, I need you to hold this. What was that? You can't read it.
I can't read it?
Cannot read it. Hi, good afternoon. My name is Mellis Cody. I'm Executive Director of Alaska Avalanche School and a proud SAW committee organizing member. The only thing more fun than being on a committee is being on a subcommittee. And I was on an award subcommittee. We wanted to start a new tradition this year. We decided we'd like to use this gathering as an opportunity to acknowledge the ongoing and enduring contributions of community members, folks that have made a big impact in improving community snow safety. Their dedication, creativity, and forward thinking has helped allow our industry to better serve the safety needs of our community. So I present you with the Silver SAW Award. This Rouge Black SAW was generously donated by Joe Stock. He lovingly handmade this in his garage and he's used it on countless avalanche courses. It's an excellent symbol of what this award stands for. This year's inaugural recipient is Andy Moderow. He had no idea until just now that this was happening. I know Andy through his work at Alaska Avalanche School, but he is a never summer kind of guy. Actually, when you say that S word, he scowls. He might even sleep with like garlic around his neck from June and July, like silver steak in his hand. So he's really like to dedicate himself to spending year-round on snow. Usually skiing, sometimes dog mushing. just in general playing, and that immense joy it brings him. It's really important that we found through things that you've done that you want to share knowledge so that that same experience comes with very little risk to other community members. So, in his time at the Avalanche School, let me ditch this part. In his time at the Avalanche School, Andy spent countless hours in board meetings with spreadsheets, late evening beers, and sending out surveys, creating a strategic plan so we could really expand education tools across the state to bigger and more diverse audiences. In his spare time, he submits, almost without parallel, detailed observations to forecasting centers in their platform, allowing them to use that data to make really good decisions and forecasts. Andy took a month off his other job and work to do a snowbatical. And so that was a month of volunteering with the Chugach Avalanche Center as a dedicated field partner and conducting his own research. So, here we are. When the idea of this award came up, it made us easy to select Andy as its first recipient. His contributions to contribute to our community outside his normal life, his normal work life, are extraordinary. Andy's spirit as the first recipient will inform and infuse this new tradition. Thank you, Andy. One more thing I say. I know he wants to leave with this really big sock, but we're going to display that one, and much to your disappointment, we're giving you this much smaller sock.
That's a good long sock.